Let's start. Hello, everyone. I will speak about FreeVol++, which is a 2D finite volume solver inside the FreeFEM. This work was done with Frédéric Echt, Nicolas Séguin, Denis Dutir, and Pierre Jolivet. So I will show you some novels about this, and okay. So I will put some example about FreeVol using advection equation, shallow water system, how to compute the gradient for higher order scheme, and how to mix finite element and finite volume. At the beginning, we have omega, the domain, th, the triangulation of omega, and eh is the set of edge of triangular th. So this domain in red is set omega e. It's contain all the points that are close to the edge A and not close to the other two edge. So here if you have discontinuous element, we have WEL, omega EL for the left triangle and omega ER for the right triangle. And now we have a finite element, so P0 for the triangle, on the triangle, it's a constant on the triangle. P0 edge omega E, it's a constant on the left and the right on the edge. So when we have this finite element, the edge is seen twice when we are passing through the triangle. And P0 edge DC, we must put we must load element PK edge to use this finite element. So this one, each edge is seen once with this finite element. We have some keywords in FreeFEM. The area, which gives the area of the current triangle. QF order for the Gauss formula. Here will be equal to 1. Len edge is the length of the current edge of the current triangle. Edge orientation, we need to know the orientation of the edge. So we have edge orientation, which is -1 or 1. Anti on edge is the number of triangle on boundary edge. So if it's on the boundary, we have only one, and if it's inside, we have two adjacent two adjacent triangle. If we want to see if we are on the internal edge, so we have the keyword internal edge. And if you want to see if we are on the boundary edge, we have the keyword boundary edge. We are interested also to see if we are on the current triangular L, for example, what is his adjacent triangular and the value of on the adjacent triangular. So it's given by other side. And at the end, the int all edge, as it's written, it is integral on all the edge of the triangle. And the function jump is for the jump of u across an edge. So it's UR minus UL. So when we have this formulation or this function, sum over all the triangle T, integral on the boundary dt, that u times v. So we can write it like int all edge, th qf order equal to 1, u times v. And this is the sum of the len of the delta of the dt times u. If you have as a formula here the area of T and the len of the edge, we can use here U times V times the area over len edge. So here U and V are P0 finite element, are in P0 finite element. If you have P0 edge, so here, as I told you before, that each edge is seen twice, so we must divide it by 2. and we must also put the edge orientation when we use P0 edge. So here, for example, UR minus UL is a jump of U, and here we divide it by 2. And if we use only edge discontinuous element, so for the same formula, we don't use the divided by 2 here, because the edge is seen once only. We applied this on the advection equation in 2D, and where V is a vector with divergence, V is equal to 0. So we have this formulation that the system is equal to dt some integral over t plus some integral over t equal to 0. We integrate by parts, and we use the fact that integration over a triangle U is equal to area of T times U. So with this one, this term will be the numerical flux in our case, when we must put the epsilon edge for edge orientation, and V scalar with the normal vector on the edge, on the current edge. So the variational formulation here, we multiplied just the flux by VH here, and we build the matrix AEG with phi I in P0 HDC, and the test function is in P0. And how to write this in FreeFEM? It's load element pk edge for P0 HDC, and then var f va as it written here, phi pce int all edge for this one, edge orientation for epsilon edge, phi pcg over len edge over area, and then we call the matrix va is va v0 HDC. J'ai pas dit Siri. For the upwind flux, we have UH in P0 and VH in P0 DC. We have in finite volume this formulation for the upwind flux, where we have V scalar N on the left triangle and V scalar R on the right triangle, if V scalar N is positive, and the boundary condition, for example, this like Newman, V scalar N UH VH. So here, for the other triangle, the R, we put other side. For VR, we put other side V. And for the normal vector, we put NN, NX, N dot X, N dot Y. So we can write the same way that it is written here. V1, V2 times N positive. It's V1 times N times U. Otherwise, we use the other side of the value. And for the upwind flux, we use the int all edge, and we put internal edge when we are inside, and boundary edge for the upwind boundary condition. And at the end, we call phi E inside the edge DC, the phi upwind 0 V0 edge DC. For the CFL, with the work of Burton and al., we have infinite volume CFL condition for the delta T time step. So PT is the perimeter of the triangle, T is the area, and so we can do it like this with delta T max, sum of max VL over area inferior to 1. So it can be written in FreeFEM like this. This is, and we can use at the end the explicit Euler scheme for the time machine scheme. So here un plus 1 is equal to un minus delta T A dot the flux. And we can solve it like this. We solve the flux first, we multiply it by VA, and then we solve the time scheme. Here is the upwind scheme with for the advection with V1 is equal to Y and V2 is equal to minus X. So here we will see the rotation of this one. And all this page is a script for for the advection equation. And you can see in a few lines we can do this with FreeFEM. But if you want to do this with C++, bon courage. We have a parallel version also with the help of Pierre Jolivet. So here in the for domain, we have the rotation of the solution. And we have a new domain adaptation that is introduced by me, where the mesh follows the solution. And it's parallelized too. So for the shallow water equation, I will only present the equation without the solution. You will have the solution at the end. How to do it with FreeFEM. So here is an hyperbolic equation, and it can be written in variational formulation like this. As you can see here, with epsilon edge, the normal, and I present only some results about this method, about this equation. So here for the dam break Malpasset, here the water which are coming down, and you have here an unstructured mesh, and with the different size of mesh, and here the domain decomposition, and here the domain adaptation, and here for the full. So it works with FreeVol, and this one for tsunami waves propagation. So also I tested with this one with the domain adaptation, parallelization, and everything is okay. For the gradient computation, thanks to Denis Judich and his work and the work of Orms, we have a triangulation here. For each triangulation, we have a weight omega e. So the weight omega e to compute it is computed like this, where we have a minimization problem with Lagrange multiplier operator, lambda and mu. Once we have the omega e, we want to interpolate all the solution on the triangle that we have on P0 to the vertex. So by using also the weight omega e, so using this formula, we have the solution over the vertex using the value of the triangle and the value of the weight of the triangle. And we use the Taylor formula where in this triangle to compute the gradient here. So we need the solution on the three vertex, which are with UV1, UV2, UV3. We need the solution on the barycenter, which is in P0 here, U0. And X1, X2, X3 is coordinated of the three vertex. So here we in exact high order, and we solve this one using a least square method, where we compute another weight omega e now, which depend on the coordinated of the difference between the center and the vertex. And with this, we can now do it with FreeFEM like this. So we load a math derivative of volume fini على not finite volume P0, We build the mesh, and then we construct the matrix that will give us the coefficient of the derivative that we are searching for. We use a P0 finite element here for the solution, and the gradient has two components in P0, P0. So by calling U0x is equal to AD times U0, we have the gradient. So here you have a comparison between finite element, finite volume, so it's of order 1. And here's the CPU time. This one, 8 seconds for the building of the map, but this will do it once at the beginning. And then this one is the matrix times the vector. We show also that we have, when we use Euler implicit, so it's a time scheme in order 1, with HLL flux. When we use order 1, we have order 1, and when we use order 2, we have order 2. So for the advection equation. How to mix this one? So we have the BBM system, and which is, this is for hyperbolic, this is for parabolic, and the ABBM will be computed with FreeFEM++, and the other one with FreeVol. So we have here two mesh. This mesh, the original one, we will take the barycenter from this one, and we will build the mesh for P1 using the barycenter of the original mesh. And we use this one on finite element and this one on finite volume. How to do it in FreeFEM? So we can build the point of barycenter by using Bx, By on P0. And then we can extract the border, and we build the mesh using the point and the border. So it works, and this is what it gives on the left, the hyperbolic shallow water, and this is the BBM. So in the same time, we have a difference between them. At the end, publish this work, it's sur le feu, on fire. Une version AL que je l'ai déposée hier, mais il faut attendre qu'elle soit acceptée. Some codes will be in the next FreeFEM version. To accelerate also the code, we want to define some fluxes, some limiters using to be compiled with the C++ FreeFEM language. Higher order scheme, more validation 3D version. À la fin, puisque les pubs sont encore offerts par Frédéric avant qu'ils soient payés, I will make some pub for two works. The first work is we publish a new paper which is in 2D and 3D of solid phase change system with natural convection. So you have inside the parallelization of the code inside the toolbox. You have a parallel also in 3D. You have MMG, mesh adaptation. So this work is done with Aina, Pierre-Henri Tournier, Francky Ludens, Corentin Lotodé, and the big chef, Ionid Danaila. And you can see all this information inside this website, lmrs-num.mathsnrs.fr, and other project of my chief, Ionid Danaila. So here we see the freezing of the water. So we cool at the right border, and here the temperature is constant. And at the end, an intermediate tutorial I will do it this afternoon and tomorrow, where we will solve the wave equation in 1D and in 2D and 3D. We will use also adapt mesh, MMG 3D, para-MMG 3D, and we will do domain decomposition using PETSE, and the visualization will be with medit and paraview. Thank you for your attention, and any question. And at the end, before you are hear me, Frederic.
Okay, so
and
merci.
At the end, in Lebanon, we have some we put a photo of the president behind us. So here I don't have any photo here, but I have this photo for the president of FreeFEM++. Any question?
So thanks, George. Any question, remark before the lunch?